1 to 2. So that's a little bit of opportunity today. So we're going to start female reproduction and kind of approach it the same way as we did with the male. Look at some of the components, look at some similarities between the male and female parts that happen. And then what we'll concentrate on today is oogenesis, formation of the female gamete, and how that works. And what is really going to become apparent in looking at female systems, things are very different. There's the obvious that it's a different type of gamete, but a whole different strategy as far as the way gametes are formed. And then additionally, the female obviously has the responsibility of allowing for fertilization, and then housing the embryo of the fetus, and that's where the uterus comes in. So there's really nothing comparable to that in the male. So as we saw with the male system, the primary organ in the reproductive system is the gonad, and in the female, that's the ovary. So ovary is the female gonad, and just like it does, just like the gonad does in the male, has two jobs, one of which is to secrete hormones, so it's an endocrine organ. In females, there are actually two groups of hormones. One group would be estrogens, and those are comparable to the androgens in the male, right? That's the female category of sex hormones. And as was the case in the male, there's one major component of that group. In females, that's estradiol. About estrogens, that's basically what we're talking about. Just like in males, we talk about androgens. We're usually talking about testosterone, right? So comparable hormone in the female is estradiol. But there's another group of hormones, progestins, which includes progesterone. And that's an entirely different group of hormones. Sometimes progesterone is described as a pregnancy hormone because its job is to get the female body, especially the female reproductive organs, ready for pregnancy, and that usually revolves around the uterus, right, the structure here. Again, there's nothing comparable to that in the male. So hormones do play a big role, and what we'll find out that's also very different in the case of the female is that the hormone levels are cyclical. They rise and fall because there's got to be synchronization between the gametes produced in the ovary and the events that are occurring in the uterus. Those two structures have to kind of be synchronized in order for an embryo to have a place to go in order for pregnancy to be successful. So we'll get into that once we start getting into the physiology part. The other function of the ovary, obviously, then, is to produce gametes. And as was the case with the male, gametes have to be haploid, right? Remember, gametes always have to be haploid. You always have to have half the normal number of chromosomes, 23 instead of 23 pairs. That means there's still going to be meiosis. The female gamete is the oocyte, sometimes simply called the egg, but the strategy is way different than that of the male. Remember, in males, you have to make lots of gametes. Males have to make hundreds of millions of sperm to ensure that enough sperm survive in the female. Basically, sperm have to go from here, the vagina, through the cervix, up through the uterine cavity, all the way up to the very tip of the oviduct. Right? So basically, they got to go from roughly here to there. Right? And considering how small sperm are, it's a really long way. So that's why you have to make a lot of sperm. Because most sperm are going to die, like 99.99% of sperm are going to die along the way. Only a very, very small percentage, or fraction of a percentage, are going to finally get to where the tip of the oviduct is. And females, there just has to be one. It just has to be one gamete, right? Because that's what the sperm are trying to find. So when oocytes are produced in the female, it's much more controlled, they're much more fewer, and things have to be more highly synchronized in order for the events to occur in the female that would result in pregnancy. So it's a whole different kind of approach in that sense. And we'll focus on that in a second. We'll take a look at oogenesis and the significant differences between it and spermatogenesis. But before that, we'll take a look at the overview of the reproductive structures. So like I showed you, here is the ovary, right? The ovary is not really connected to us. We'll find out there's a space, but it's in the proximity of the uterine tube, also called the oviduct, and actually I like that name better because it more describes what it does. And it's really a duct between the ovary and the uterus. It's also called a fallopian tube. That's the old name for it. So that is essentially the duct system in the female. And the space, the lumen inside the oviduct becomes continuous with this space inside the uterus, which is called the uterine cavity. And we'll see some pictures later that kind of reinforce that. And then notice that the uterus, the inferior end of the uterus is called the cervix. Cervix means neck. It's thinner. It protrudes into the vagina. And the vagina exits the body, right? So this is part of what we then call the reproductive tract. When birth occurs, sometimes it's referred to as the birth canal. It's a continuous space between the cavity inside the uterus and the vagina and then on out. So if the baby's born normally, it goes out of the uterus to the vagina and then out of the body. So the uterine cavity is continuous with the vagina. The uterine cavity is also continuous with the oviduct. That's kind of the oocyte, and then eventually if it gets fertilized, and the embryo would travel as well. I emphasize the point when we did the urinary system that the female urethra, which is right here, has nothing to do with reproduction. It just happens to open the area close to where the vagina is. And you can see that the urethra is continuous with the bladder, just like it is in the male. But unlike in the male, there's no secretions, no contribution from the reproductive system into the urethra, which just opens where the vagina is. So you have two separate passageways, right? Urinary tract is here, and the reproductive tract is here. So vagina, cervix, uterus, oviduct, and so on. Continuous, that's what we call reproductive tract. So that's how things are kind of set up. So, as far as gamete production, right, that's going to happen in the ovary, and we'll take a look at how things are structured, and then we'll look more detail in a more detailed view of the ovary. So this is what the reproductive system looks like: the uterus, the oviducts, the ovaries, and all the things that kind of hold together. Just like we saw with the digestive organs. I talked about the peritoneum and all the divisions of the peritoneum, like the mesocolon that attaches a large intestine, and the mesentery, which attaches a small intestine. Similar extensions of the peritoneum here that stabilize the uterus and the oviducts and the ovaries. The biggest ligament is called the broad ligament right here. The broad ligament is an extension of the peritoneum, just like we have the other stuff doing that. And the peritoneum is really big. It's involved with a lot of stuff going on in the abdominal pelvic cavity, in this case the pelvic area. And the broad ligament also extends in what's called the mesovarium, which is a ligament between the ovary and the oviduct. And then notice that the ovary is stabilized on both sides, medially and laterally. Medially, there's an ovarian ligament that extends from what would amount to be kind of the body of the uterus to the medial part of the ovary. And then laterally, there is the suspensory ligament that goes from the lateral end and up into the abdominal wall, right? So everything's kind of held in place and stabilized. Meanwhile, down here, there's what's called a uterosacral ligament. There's also a round ligament somewhere down there. So everything is kind of held in place. And what that really amounts to is in the pelvic cavity, right over top where the bladder is. So the uterus kind of sits right over top of the bladder. What we'll find out later when we look at pregnancy, the latter stages of pregnancy, like the last trimester, the uterus gets really big because the fetus grows. And then the uterus pretty much displaces a lot of the abdominal organs, pushes things up and over and down as it grows. But when it's not pregnant, it just sits right on top of the bladder like you can see in that picture. Okay, so that's where all the reproductive structures are found. What we're going to concentrate on today is what's happening in the ovary. This is what the ovary looks like. Again, here you can see the ligament connects to what's called the hilum of the ovary. This egg nest, we'll talk about that in a second, is where most of the premature oocytes are found, and then from there they develop through a whole process. But unlike sperm formation, where the sperm are pretty much on their own, they obviously get help from the nerve cells, oocytes develop as part of a bigger structure called a follicle. So we're going to be looking shortly at what we call the ovarian cycle, which not only goes through oogenesis, but it also involves the accessory structures around the oocyte, which are part of what we call follicle. So ultimately, what grows in the ovary is a follicle through different stages. It becomes mature, and then it ruptures, and it releases the oocyte. That's what we call ovulation. So we'll take a look at how that process works. Okay, so here's the big picture. Here's oogenesis. And there are some similarities, just like in spermatogenesis. We have to make haploid gametes. So gametes have to be haploid, because when they fuse during fertilization, that's where the diploid number comes from. Right? So found female gamete have to be haploid. But other than that similarity, that's pretty much where it ends. I mean, everything else is very different in the case of oogenesis, all the way up through the meiotic divisions, up through how it's controlled, up through the speed with which it occurs. You know, everything is very, very, very different. Okay, so let's take it step by step and see what oogenesis involves. So, there is mitosis, but notice when it occurs. During fetal development, and that's it. That's when the mitosis of the oogonia occur. You know, comparable cell in the male, remember, was the spermatogonia. But in males, once a male hits sexual maturity, spermatogonia continue to undergo mitosis continuously, right? There's always an ongoing supply of cells ready to go on to form sperm. Not in the case of the female. This only happens, right, during fetal development. So by the time birth occurs, there are already a finite number of primary oocytes in the ovary. That's where that egg nest is that we just looked at, right under the surface of the cortex. As far as numbers are concerned, roughly maybe 1 million or so are there at birth. By the time a woman hits sexual maturity, hits puberty, that's roughly half, maybe like 500,000 or so. That's still way more than can ever be released, because what we'll find out is the ovarian cycle involves the release of a gamete roughly every month. And if you extrapolate that to a female's reproductive years, remember females do have a more distinct menopause, where the ovaries stop releasing oocytes and oogenesis stops. That's roughly, maybe from early teens up through roughly 50, early 50s or so. And approximately 500 gametes would be released during that time, roughly 1 month. Right? So the numbers are way more than ever going to be needed, but as far as comparing that with sperm, a male makes more sperm in a few minutes than a female does for her entire life. I mean, that's how different it is. Right? It's a different strategy. So oogonia are only going to go through mitosis. They're still diploid cells, right? It's still just mitosis. There's no meiotic division. There's no reduction of chromosome number. It's still regular old mitosis. Cells are diploid. But by birth, the oogonia have developed into these primary oocytes. And as we saw earlier, they're found clustered in an area of the ovary called the egg nest right here, just under the cortex. That's where all the oocytes accumulate. Now, the other thing that happens throughout the reproductive cycle of the female, in reference to oocyte, is every year a certain percentage of the oocytes undergoes what's called apoptosis. Right? What apoptosis is described as is kind of programmed cell death. Right? The cells that don't go on to the next stage of development, as far as ultimately forming mature gamete, they simply go away. They die, they get reabsorbed. So this is why every year, once sexual maturity arises in the female, the amount of oocytes continues to go down with apoptosis. But so there's still plenty there, just way, way, way fewer. So roughly 1 million at birth. By the time puberty, roughly half of that, 500,000. And then every year a certain percentage undergoes apoptosis. Okay? So very different as far as the amount of gametes there. Now there's new research. They've looked at mice. They've also looked at humans, and there's maybe an outside chance that there is some type of development after that, but it's too early to say for sure whether this theory doesn't work. So as of now, the accepted theory is that there's a finite number of oocytes. All that are ever going to be there are there, and there can't be any more unless somebody proves something different. So notice that by the time birth occurs, the oocytes have already undergone very early stage of meiosis 1, but no farther than prophase, which is the first stage. And when we talk more about meiosis in detail, we'll find that one of these significant events in meiosis 1 is the formation of things called tetrads. But I don't want to get into the details of that now. I'd rather wait until we cover genetics, and we'll talk about it in the context of recombination and what the advantages of meiosis are. But at any rate, the primary oocytes are there at birth. Begun meiosis, but stop in prophase of meiosis 1, and that's it. Right? So that's what's there at birth. So numbers roughly 500,000 or so scattered throughout the ovaries. So now hormones become important. Right? We looked at hormones in the case of the male the other day. We talked about the HPG axis, right? Hypothalamus, anterior pituitary, and the gonad. And that's certainly the case in the female. In the female, it's very cyclical. I've been using that term. What that means is hormone levels are going to change through roughly a monthly cycle, about 28 days on average. It can be a week earlier than that or a week ahead of that. I think about 20% of women have roughly a 28-day cycle. Others a little shorter, a little bit longer. But at any rate, it's cyclical, right, in that time period. So there's the ovarian cycle and then the uterine cycle. The ovarian cycle is where oogenesis occurs along with the development of the follicle. And the driving factor in that is the anterior pituitary hormone called FSH. Right? Remember, FSH stands for follicle stimulating hormone. Right? And the follicle, again, is what the oocyte is part of. But FSH is also needed to continue the progression of the oocyte through meiosis as part of oogenesis. So at puberty, remember FSH really isn't going to be there until puberty starts. And then it's the same relationship, the GnRH, as we saw with the male, that's the H part, the hypothalamus part. GnRH triggers the secretion and release of FSH. And as FSH levels rise, then that triggers some of the primary oocytes to begin meiosis 1 that could continue on. They already stopped in prophase, but under the influence of FSH, some of the primary oocytes will continue on and complete meiosis 1. Now, even though we're talking about a cycle being roughly a month, 28 days or so, it actually takes much longer for the follicles to go through this whole process. So there's always got to be a set that are in the process of going through this development so that some can ultimately make it to maturity within that period of time. So ultimately, each ovarian cycle is going to result in the production of what's called a dominant follicle. There's competition within that egg nest, and some of the follicles are going to respond better to FSH and continue on and continue through oogenesis, and then ultimately, generation 1 is going to make it all the way within that monthly cycle. So FSH becomes really important for that process, not only to develop the follicle, but to stimulate some of the primary oocytes to undergo meiosis. So when a primary oocyte undergoes and completes meiosis 1, notice that it's an uneven division. Another big difference, right? In the case of the males, one primary spermatocyte always produces 2 secondary spermatocytes, right? Not in the case of the female. It's unequal. One cell, called that the secondary oocyte, gets everything. It gets all of the cytoplasm plus the set of chromosomes. Right? Remember, this is the reduction division, just like it was in the male. The secondary oocyte is haploid. And we can kind of see that. This tetrad, as it's called, is actually 2 chromosomes that are attached. Each chromosome has 2 chromatids, so you have 4 chromatids, what's called a tetrad. Right? So that's still diploid. But when the primary oocyte undergoes meiosis 1, the chromosomes separate, right? That's what meiosis 1 does. So the secondary oocyte is a haploid cell, even though each chromosome still has 2 chromatids. Right? It's still considered an unpaired chromosome, so this is haploid. But notice what happens in the other case, right? It's called a polar body. The unequal division means that all of the cytoplasm goes to the secondary oocyte, and no cytoplasm goes to the polar body. That's why it's not called a cell. It's just the extra set of chromosomes. So those chromosomes are discarded, right? Remember, they have to leave the cell, otherwise the cell's still technically diploid. And it may divide, it may undergo meiosis 2, or it may not. It doesn't matter because it's not functional. It's not a viable cell. It can't get fertilized. So it's just discarding the chromosomes. So the secondary oocyte is the stage of oogenesis where the oocytes release from the ovary. We call it ovulation. Right? We'll see what that looks like shortly. Right? And unlike sperm, which get progressively smaller, the oocyte is actually really big. Right? And to put it in perspective, you can barely see sperm even with a strong microscope, even using that high-power oil lens at about 1000x. You can pretty much see an oocyte with the naked eye. It's about the size of the head of a pin, so it's much, much, much bigger. So it's the cell that they call the cytoplasm. So that's a cell that's ovulated, and when it's ovulated, it has begun meiosis 2. However, it stops midway through. Right? When it leaves the oocyte, or when it leaves the ovary as a secondary oocyte, it's in metaphase. Right? right, of meiosis 2. Hasn't completed meiosis 2 yet. It's not the metaphase midway through. Right? So here's where things become really different. The only way that the secondary oocyte is going to reach maturity and become a sperm ovum is if it gets fertilized. If the sperm penetrates, the first thing that the secondary oocyte has to do is complete meiosis 2. And then it expels a second polar body, keeps one set of chromosomes, that's going to become the nucleus of the ovum. And then that's what is going to merge its chromosomes from the sperm. That's fertilization. Right? But it's unlikely that that's going to occur. If it doesn't occur, then the secondary oocyte never completes meiosis. It stops in metaphase, and that's exactly where it stays. And it lasts for maybe 2 days. It gets expelled from the ovary into the oviduct. We'll take a look at what that looks like shortly. But within about 48 hours, it loses its viability, it disintegrates, and it simply gets reabsorbed somewhere in the oviduct. So the only way that you really complete oogenesis, technically, is to have fertilization. Yeah?
If it's not fertilized, does it stay diploid?
It's still haploid. No, it's haploid. This is already haploid. After meiosis 1, the secondary oocyte is already haploid. So it's still a haploid cell, but if it doesn't get fertilized, it doesn't last. It doesn't live. It slowly makes its way through the oviduct, but if it doesn't get fertilized, it's got about 48 hours of viability, and then it stops, and it loses it, and it simply disintegrates. Okay. So this is why the sperm is shown in the last diagram, because in order to complete oogenesis, in order to finish meiosis 2, it has to be fertilized. You know, and we'll look at the events of that a little bit more closely when we look at fertilization. You know, there are various things that have to occur. What happens is, as soon as the sperm penetrates the oocyte, there are things that happen to lock out the other sperm, and the oocyte becomes very different. But this penetration then triggers the events that then cause the complete meiosis 2. It has to be there, right, to get rid of that second polar body. So there will be a second polar body, but only if the secondary oocyte gets fertilized. If it doesn't, then there's not really ever going to be a second polar body, and as I said, the thing just disintegrates. Okay. So it's a hugely different process, other than the obvious, right? You're making oocytes instead of sperm, but it's regulated, takes much, much longer. It results in the production of one functional gamete roughly every month. That's it, right? But that's all there has to be, because the sperm then have to fertilize that. Again, you need a lot of sperm, because in order for sperm to reach this point, you have to have huge numbers, because the vast majority aren't going to last long enough. They're not going to make it that far to even have a chance of fertilizing. So that's why female can just make one gamete per month, and that gamete's what it's going to get fertilized. Right? So here's a comparison of oogenesis on one side with what's happening in the ovary on the other side. Right? So again, you can see the unequal divisions, and it doesn't. Oh yeah, it does say before birth. So make sure to understand that as far as the big picture, as far as oogenesis, the only place you get mitosis is in the ovary, but before birth, during fetal development. Right? That's when the supply of potential oocytes is built up. And by the time birth occurs, they are oocytes. I like this diagram because now it shows the haploid versus diploid. Right? So when the primary oocyte completes meiosis 1, right, forms a secondary oocyte, you can see these cells are N, and remember means haploid. Right? So once the cell's haploid, then it stays haploid. You can't increase the number of chromosomes after that. That's the focus. But it's a secondary oocyte that is released from the ovary during ovulation, and that's what has to be fertilized, and only if it gets fertilized will it complete meiosis 2. So now let's take a look at what's happening on the right side. Follicle developments. Right? I mean, again, sperm are pretty much on their own, right? Sperm are formed in the seminiferous tubules. They're released into the tubules. They travel through a duct system. They do get help as they're developing from the nurse cells, right? But the nurse cells are just in the testes. They're not released along with it. In the case of the oocyte, there's a lot of accessory cells that stay with the oocyte, even after it's released from the ovary. So here is follicle development. And this should look familiar. When we had lab last week, you were looking at ovary slides, and hopefully you saw within the ovary slides various stages of follicle development. The follicle really has 4 different stages that can be identified. right? Primordial, primary, secondary, and then mature follicle. And the mature is the stage right before the oocyte's released. Okay, so take a look at that. So all of this is under the influence of FSH, right? FSH is a hormone for the anterior pituitary. It stands for follicle-stimulating hormone. And that's exactly what it does, right? It stimulates the development of the follicle. So in the ovary, in that area called the egg nest, like you can see here in front of the cortex, there are lots of what are called primordial follicles. You can see a closer look at a primordial follicle. A primordial follicle is a primary oocyte. Again, in meiosis, in the very early part of meiosis 1, prophase, surrounded by kind of a loose layer, what are called follicle cells. Right? And I say loose, meaning it's not really continuous and it's not flat. Right? So that's what the majority of the oocytes look like in the ovary. In this area called the egg nest, in the form of what are called primordial follicles. But if you look at what's happening in the ovary, and again, this takes a lot longer than a month to go through the whole stages, so there's got to be an ongoing supply of follicles that are in various stages of development. Some of them become what are called primary follicles. And the difference between a primary and a primordial follicle is in the distribution of the cells around the oocyte. So here's the oocyte. Specifically, this would be the primary oocyte, right? We haven't completed meiosis 1 yet. But right outside the oocyte is a ring of cuboidal cells, each of which is called a granulosa cell. This is what we call primary follicle. So primordial follicle is a loose layer of kind of flat cells, not especially organized. The cells are called follicle cells. Under the influence of FSH, every month some primordial follicles continue on and become primary follicles. So now the cells are more cuboidal, right? They make a concise ring, a continuous ring around the oocyte. What these granulosa cells do is they form gap junctions with the oocyte, so things can get passed back and forth and there's communication. They also communicate with cells that are in the ovary. You can see that was the top of they're called thecal cells. Right? So the thecal cells are not actually part of the follicle, but they're right next to it. And they also communicate with the granulosa cells. So the thecal cells and the granulosa cells get together to begin to secrete estrogens, like estradiol. And this is where the secretory activity in the ovary comes from. Right? Remember, the ovary has two jobs: it's got to make gametes. It's also got to secrete hormones. So this is where the hormones come from. So the thecal cells kind of pass on the raw materials to the granulosa cells. Raw materials are things like cholesterol; these are steroid hormones. And then the granulosa cells begin the secretion of estrogens. Now later on, we'll look at graphs showing you the rise and fall of hormones during the cycle, and you'll see that as follicle development occurs, as we go from a primary follicle to a secondary follicle to a tertiary follicle, there's a buildup in the level of estrogens. The level of estrogens continues to go up during that first half of the cycle. So we'll see that graphically down the line as well. All right, and notice that in this picture there are two primary oocytes right next to each other. So like I said, it takes longer than a month. So there's always an ongoing supply of follicles that are continuing on through not only oogenesis, but follicle development. Right, but inevitably one of these primary follicles becomes, I used this term earlier, a dominant follicle. And that means it is the one that's going to respond most vigorously to FSH. Probably has better receptors, right, some kind of chemical reaction where it's going to grow a little bit faster. And its granulosa cells will continue to reproduce. They can divide, right, unlike the oocyte. And now you get multiple layers like I showed in picture 2. So as soon as you have a second layer of granulosa cells around the oocyte, it's going to get something that looks like this. Right? So now we no longer have a primary follicle, now we have what's called a secondary follicle. Got to be at least 2 layers, sometimes there's more than that. And the other distinguishing feature, this picture shows that pretty well, is that as those cells continue to secrete those estrogens, obviously some of them have to be absorbed because the blood level of estrogen goes up, but some will accumulate as little pockets of fluid. And that's what the white spaces are in the picture, right? Little pockets of fluid that start to accumulate. So you also see that as the latter stage of a secondary follicle. Not only multiple rows of cells around the oocyte, but these little white pockets. Right? So as that continues, the structure gets bigger. If you look at the scale, this is like 1,000 times magnified. This is only a little over 100. So this is way, way, way bigger. Right? That's why you see that something like that in this picture. You see that pretty well as well. This is what's called a mature follicle, or a tertiary follicle. Also sometimes called an antral follicle, because the cavity that develops is called an antrum. Right? So these little pockets, right, all this white stuff starts to merge, forms a big pocket fills what's hopefully fluid, which is going to contain things like estrogen as well. Right? So that starts to grow. So what you basically have is one side of the follicle becoming kind of thin. And notice this is right at the surface. I mean, this space right here is outside of the ovary. So this is happening right under the surface of the ovary. And that thin part of the follicle bulges. This picture shows a little bit better right here. Right? The thin part of the follicle bulges away from the ovary. Right? And this has all been under the influence of FSH. The dominant follicle, there's just one of those, is going to continue on. It's going to respond to the hormones. It's going to make it to maturity. Others that are less dominant will undergo apoptosis, and that's why there's diminishing number of cells that go through. Now another hormone becomes significant, right? There's another anterior pituitary hormone. It's called LH. You mentioned that with the males, and LH in males promotes testosterone secretion. LH in females, LH stands for luteinizing hormone. You remember the hormones are named after what they do in female, and that has to do with this thing called corpus luteum. But the major effect of LH is that it kind of surges mid-cycle, right? And if the cycle is, let's say 28 days, roughly day 14, there's a huge surge in LH. The concentration of the blood goes way up. And one of the things that LH does is it promotes increased blood flow to the outside of the follicle. The follicle wall softens, and then it pops, it bursts. And that's what ovulation is. Meanwhile, there's some other pretty significant changes right around the oocyte. Yeah, here we go. So here's the oocyte, right? Now it's a secondary oocyte. Somewhere between the transition between secondary follicle and mature follicle, it completes meiosis once, so now it's a secondary oocyte. It starts to develop this clear layer right around the surface of the oocyte, right? Like this dark line, that's the membrane of the oocyte. This clear layer is outside of that. It's called the zona pellucida. And it's something that the oocyte makes. It's kind of glycoproteins and other molecules that accumulate and form this coating around the oocyte. It's called the zona pellucida. And that's going to stay with the oocyte even after it's released from the ovary. And then just beyond that are some of the granulosa cells right here, and they form what's called a corona radiata. So you have the secondary oocyte right here. You can see the nucleus of it. Right? Again, the dark is the membrane. The zona pellucida and the corona radiata. There's almost like a little stalk that connects those cells to the remaining granulosa cells that are part of the follicle. And then the dominant feature of the follicle again is this big thing called an antrum. So here we see both labeled in that picture, right? So secondary oocyte, zona pellucida is the clear area. That's labeled in the top picture as it's forming, and then the corona radiata. The significance is that's what's going to be released, right, when the follicle ruptures. So LH promotes increasing blood flow, almost like a kind of inflammatory response. It softens the surface of the follicle, and then the follicle ruptures, right? And again, roughly mid-cycle. Sometimes a woman can get a little twinge of pain. There's a German name for it, it's called Mittelschmerz. And sometimes a woman can actually feel that because it literally bursts the surface of the ovary. So what's released then is the secondary oocyte, the zona pellucida, and the corona radiata. But the rest of the follicle isn't just discarded, it has an important job. It kind of reorganizes, right? Like all of this stuff becomes a corpus luteum. Right? Corpus luteum means yellow body. It looks like a yellow spot. And one of the reasons it's yellow is because of all the cholesterol it accumulates to make steroids. Because the job of the corpus luteum is to secrete the other group of hormones, which includes this one called progesterone. Okay, so now that's the focus of the second part of the cycle. So sometimes the cycles are called by different names: pre-ovulatory, post-ovulatory. The second part is sometimes called the secretory phase or the luteal phase. But the bottom line is that now this is the dominant hormone, the progesterone, and it comes from the corpus luteum. Right? Meanwhile, the oocyte is released. I'm going to flip ahead here to show you what the oviduct looks like. So when ovulation occurs, here's the ovary. Right? The oocyte would be released along with the zona pellucida and the corona radiata. It should be drawn into what are called the fimbriae, which are these finger-like projections at the beginning of the oviduct. It can be cilia, and then it starts to move very slowly down through the oviduct, right down toward the uterine cavity. But notice how there's really not any continuous structure between the ovary and the oviduct. So there's no saying, there's no guarantee that the oocyte won't just be lost in the abdominal cavity. Right? I mean, more than likely, it's going to make its way to the fimbriae. The fimbriae do have cilia; they create kind of a current to draw it in there. But there's no saying that that has to happen for sure, right? With guarantee. And I don't know what the percentage is. I mean, I'm sure it happens time to time. That it simply doesn't make it in the oviduct. Just go down. Right? So there's like in the case of the sperm are always in a tube, right? They're kind of protected. They're always in the lumen of the tube until they're released from the body. But there's a little gap that the oocyte has to overcome to get into the oviduct. So it's a little bit different as far as kind of the structure that way. Okay, so what the corpus luteum does is it makes progesterone. Progesterone is sometimes called a pregnancy hormone because that's its job. Its job is to get the reproductive system ready for pregnancy in anticipation of there being an embryo, right? If fertilization happens, then the uterus has to get ready to receive the embryo. If we go back and look at the oviduct, if fertilization is going to happen, it's generally within about the first third of the oviduct, between the area called the fimbriae and the area called the ampulla, right, roughly in there. So to put that in perspective, sperm, going to have to move from here, through here, all the way up there, right? It'll go a long way. That's why sperm have to be streamlined, and that's why the numbers are important, because most of them are going to die along the way through that. And the reason that it's important for fertilization to happen in that first part of the oviduct is that it takes about a week or so, almost 2 weeks actually, to get the uterus ready to receive an embryo. By that time, the embryo will have divided repeatedly and be in the form of a cluster of cells instead of just one by the time it gets to the uterine cavity. So progesterone is going to thicken the lining of the uterus. It's going to cause the lining of the uterus to build up so that when an embryo does get to the uterine cavity, it might float around for a day or two, but then it's going to stick to this lining called the endometrium, and that has to be what's called implant. Right? And that's required to sustain it. So if we go back and look at the uterus or the ovary and what's happening, right? We expel the secondary oocyte and the corona radiata and the zona pellucida, so where that's going to go. The rest of the follicle becomes the corpus luteum. It makes progesterone. So either of two things are going to happen at this point. Either the embryo is going to, or the oocyte is going to be fertilized, and then there's going to be an embryo. So the embryo has to make a really important hormone. As soon as the embryo is formed, it makes something called HCG. And this is actually what pregnancy tests look for. Right? Nowadays, you do a pregnancy test simply by, I guess it still requires urine. I don't know if there's anything less invasive than that. But basically, what pregnancy tests look for is this hormone that's only present if you have an embryo, HCG. And one of the major jobs of HCG is it helps to maintain the corpus luteum, how it keeps it there. Because if there isn't any signal, if there is no embryo, there's no HCG, the corpus luteum will, within about 10 days, stop secreting progesterone. It will only last for about 10 days, it will make progesterone during that time. But if it's not told to stay there by HCG, then it stops. And when there's no longer any progesterone, then that affects the lining of the uterus. The lining of the uterus breaks down because there's no pregnancy, and then the whole cycle repeats. And then next month, another gamete gets released. But if HCG is there, then the corpus luteum stays for roughly the first 2 months for pregnancy, most of the way through what's called the first trimester. And again, the focus is on the lining. The lining has to be thick, it has to be vascular, it has to be glandular in order to maintain the ability to hold on to the embryo. So this is why synchronization is really important. What we're looking at here is called the ovarian cycle. Right? And the focus of the ovarian cycle is to have a follicle go through the various stages of development, right, from primordial to primary to secondary to mature. Again, it takes longer than a month, so there's always got to be kind of a head start. There always have to be follicles in various stages of development. But the one that reaches maturity is the one that's going to release the oocyte, and the oocyte then either is going to be fertilized or it's not. Right? And that determines then what happens in the uterine cycle, and that's going to be influence of progesterone. So if there is pregnancy, the corpus luteum is going to stick around for a few months. If there isn't pregnancy, then the corpus luteum becomes a scar called the corpus albicans. It's just kind of a white scar, white spot of connective tissue. And when you look at ovaries like are shown here, they're usually shown kind of bumpy and kind of white from the outside. And that would be what ovaries look like of a woman in sexual maturity. Every little white spot is a place where an ovary, where an oocyte had been released. There had been a corpus luteum, and the corpus luteum shuts down and turns into scar tissue that becomes a corpus albicans. So that's kind of the cyclical part of that. So this both pictures show schematically the progression in the ovary. I mean, like I said, you won't really see an ovary with all these different stages at once. You'll see lots of primordial follicles in that area called the egg nest. If it's a ovary where ovulation is imminent, then you'll see a mature follicle at the surface, but you really won't see all the different progressions at the same time. You're just going to look at that sporadically. And notice that the oocyte and all the accessory things making the follicles, those are in the cortex of the ovary, again, right under the surface in the area called the egg nest. The middle, the medulla of the ovary, is basically where the blood supply is. The ovary has to be vascular, all this stuff needs energy, so there's going to be a blood supply. But that's pretty much coming into the middle, and then the stuff as far as the function of the ovary, making gametes and making hormones, that's happening kind of in the outermost part of it. Okay, so that's ovulation. So let's take a look at the oviduct, see what that looks like, and then kind of wrap up. So the oviduct, uterine tube, fallopian tube, whatever you call it, is essentially the duct that's going to move the oocyte down toward the uterus. That's one of its functions. The other function of the oviduct is, as I said earlier, fertilization. Right? Really important that fertilization happen roughly in the first third, so you have that 10-day or so lead time for the follicle or for the embryo to be developing as it travels down to the uterine cavity. Fertilization really can't happen in the uterine cavity. In fact, that would be virtually impossible because it's so big. Right? Owing to the size of the sperm and the egg, even though the egg's much bigger, there's virtually no way for the sperm to find the oocyte in the uterine cavity. It's much more likely to find it up here. You're talking about a more narrow passage, right? And this is what the oviduct looks like. This is the lumen. It does secrete a kind of a nutrient fluid. It's mucin-secreting cells, meaning there's carbohydrates and so on in there that the oocyte can also absorb, even though it has a lot of cytoplasm. There's a lot of energy that goes into the cell division. And then the ciliated cells create the current that gradually moves the oocyte and the embryo down toward the uterine cavity. Meanwhile, there's smooth muscle around the uterus. One of the theories is that the smooth muscle can also contract to help sperm make it faster to the beginning of the oviduct. That the sperm, having prostaglandins and things like that, they stimulate smooth muscle contraction and make these kind of peristaltic waves help to pull the sperm up toward the beginning of the oviduct faster. Right? Studies have shown, based on the rate at which sperm swim, they get to the beginning of the oocyte or beginning of the oviduct much faster than they ordinarily should. So that should be that's possibly a function of the smooth muscle that's in the wall of the oviduct. All right, so we'll wrap up there for today. On Friday, we'll then switch over to hormones and talk about HCG and LH.